Hi guys, this is Chris Allen. I am going to try to go through section 6.2 here with you very quickly. What I've done is you have a copy of these notes. I'm going to give you the answers to most of these problems and show some of the work, but I'm going to focus mainly on the examples. So for the warm-up, just to let you know, this was calculator allowed. The first answer for the warm-up, this area, turn my pen on. This area would be 6.400. The second one, I ask you to write just the integral without the absolute value. So really what you got to do is you got to deal with this guy right here. So I'm not going to give you the full answer, but I'll just tell you that this curve is really what we call a V-shaped, right? Because it's absolute value. So it's going to have, let's see here. Looks like it's going to have its vertex at 1, 2. So it's going to be, this shape curve right here is the vertex at 1, 2. So you have to break it into two pieces at x equals 1. And of course, this guy over here, the equation is going to be y equals negative x plus 3. You would have to check that. And then this curve over here is going to be y equals x plus 1. And then you're going to have to write the integral. It's a couple of pieces, and if you really want to know what the answer is for this, the answer for this area turns out to be 24. Okay, so we're going to look at something called the disk method and the washer method, and I'm going to do a couple of examples of each. So the disk method is based on disks, and I'm going to kind of just jump to the point here. Here is the formula, and you'll notice that the formula looks an awful lot like pi r squared. So I'm going to go ahead and do the first example here. We're trying to find the volume of the solid form when revolving this curve, square root of sine x, about the x-axis. So here is the graph of y equals the square root of sine x. And we're going from 0 to pi as suggested in the problem. So this would be the shape the volume would make. So here's how this would go. We're just going to say that the volume is going to be pi integral from a to b of r squared dx, where r is the function. So in this particular problem, maybe make it in a different color, it's going to be going from 0 to pi, because that's where we're starting and where we're finishing. And then we're going to do the square root of sine x, but then it says we need to square that dx. So now I'll just go ahead and quickly work this one out manually. Of course, when you square a square root, the square root goes away. And then you get pi, and then negative, and then this would be cosine x. And you would evaluate the antiderivative at pi and 0. You end up getting negative pi times the cosine of pi minus the cosine of 0, which ends up being negative pi times negative 1 minus 1, which is negative and a negative, which makes a positive 2 pi. So the volume of this region here, that's this guy, would be 2 pi units. So that would be the volume. Now here's a student practice one. I'm going to let you guys do this one on your own. I'll just give you the answer. I'll give you the decimal answer since it says calculator allowed, and you'll get 49.009. That's the volume I got for this one. Okay, so that's the disk method. By the way, this is what this particular graph, you would have this parabola here, and of course we're rotating it around the x-axis. Okay, so I now want to mention something called the washer method. So we did a disk method, a couple of examples of that. The washer method is the same idea, except now we're going to do two disks. We're going to find this inner disk, and then this outer disk. We'll find those volumes separately, and then we'll subtract them. So it's kind of like when we're trying to find the area between two curves. You take the top curve minus the bottom curve. It's the same idea. So the formula is a little bit more developed, but it's essentially the same thing. It's still pi r squared. It's just what you're going to do is you're going to take your outer radius and then subtract your inner radius, and each of those things are squared. So now let's go ahead and look at this example. So here are our two curves. we've got our outer radius is the square root of x. We've got our inner radius, which is x squared. We're going to rotate this around the x-axis, so this would be the shape it would make. And now we want to know what the volume is going to be. So to find the volume here, we're going to do volume equals pi integral. Now I need to check. It looks like we're going from 0 to 1. So that tells me, well, here, let me write the formula down. Big R squared minus little r squared dx. And in this particular problem, it's going to be pi integral from 0 to 1. Big R was the square root of x squared, and then little r was x squared. So this is the integral that we're going to use on this problem. And if you guys don't mind, I'll let you simplify it and find the, fill in the details. I'll just kind of put ... The answer turns out to be 3 pi over 10. You could do this manually or with a calculator. I'm just going to go ahead and give the answer here, because once you get the integral is something that we've already been doing since chapter 4. So that's example 2. That's a washer method. Big radius squared minus little radius squared. Student try. So here's another example for you guys to try. I'll give you both the exact answer and the decimal answer, and then I'll do my final example. I'm trying to keep this video under 10 minutes. So the volume here turns out to be 128 pi over 15. That's the exact area, or I'm sorry, the exact volume. And then the decimal turns out to be 26.808. And now for our final example. Our final example is based on the previous one. So if we go back to this slide here, we've got this shape here. But in this example, in example 2, I was rotating around the x-axis. Now if you look at example 3, it says rotated around the y-axis. So essentially you've got this same curve here. You've got this square root of x function here, right? This is the square root of x. And then you've got this other curve here, which is like this. And this is, this one's a line. It is not a curve like that. I'm thinking of the wrong part. This one's a line segment like this. So this is y equals 1/4 x. And this is the region we're rotating, this region right here. And we're going to rotate this around the y-axis this time instead of the x-axis. So this is going to require us to use a slightly different version of our formula, which I'll write here. And that would be pi integral from c to d of big R of y squared minus little r of y squared dy. So here what we're doing is we're integrating with respect to the y-axis, and I'm squaring this outer radius and I'm squaring this inner radius function. So that requires us to adjust this curve to x equals 4y. So now I've changed, instead of y equals, I wrote as x equals by multiplying both sides by 4. And let me clean this guy up here. And of course, this guy here is y equals the square root of x, so it's going to be x equals y squared. You'll also notice that the outer curve, this is now the big R. It was the little r in the first problem, and now it's the big R. And of course, this guy's going to be the little r. So it's going to, we're still going from 0 to 1. This is 0, and then it's going to go up here to 1, so that's not changing. So we're going to integrate from 0 to 1. Our big R, which we said is this, is going to be 4y quantity squared. And then this here is going to be our little r, so that's going to be y squared dy. You'll notice that everything now is in terms of y because we're rotating this around the y-axis. And let's see what our final answer here turns out to be. Again, I'm speeding this up because I'm trying to keep this under 10 minutes. There's the volume. And that brings us right to 9 minutes and 30 seconds. So I would encourage you to finish these notes, spend some time reflecting on them, and then start working on practice. I think I've posted some other videos, but that makes it under 10 minutes.